All right, welcome to this explainer. Look, if you hear the word biostatistics and immediately picture, I don't know, endless dry math equations, I want you to literally throw that image right out the window. Seriously. Instead, think of biostatistics as a thrilling detective's toolkit. It's this rigorous, totally fascinating method we use to uncover hidden truths in medical research. It is exactly how we take raw, messy clues from the real world and extract actual life-saving conclusions. So let's grab our magnifying glasses, dive right into this, and see how the whole shebang works.
Here's the roadmap for our data journey today. We're going to demystify these complex processes step by step. 1. The language of data. 2. Describing your sample. 3. The leap of inference. 4. Testing the hypothesis. And finally, 5. Choosing the right test. Let's get into it.
So, we arrive at the core question of literally any good detective. How do we actually learn from the data? At its heart, biostatistics is the art of measuring, controlling, and communicating uncertainty. It's how we systematically approach real-life medical mysteries, parse through all that noise and conflicting suspect testimonies, and emerge with a concrete, reliable answer. An answer that doctors and researchers can actually use to treat patients.
Now, to answer that core question, every researcher follows a very specific life cycle. First, you state a valid research question. What crime are we trying to solve? Second, you collect and clean your data, kind of like dusting for fingerprints. Third, you perform exploratory analysis just to get a feel for what you're looking at. Fourth, the formal analysis, bringing the suspects in for questioning. And finally, you interpret those results and confidently draw your conclusions.
Okay, Section 1, the language of data. These are our foundational clues. Before we can solve anything, we need the right vocabulary.
The absolute crucial point here is understanding the difference between a population and a sample. The population, that massive crowd you might picture, represents the ultimate truth we want to uncover. Imagine wanting to know how a new heart medication affects literally every single patient in Ethiopia. Tracking every single one of them down is, well, it's impossible. So instead, we put a magnifying glass over a sample, a smaller, manageable subset of people. The entire goal of biostatistics is to interrogate that small sample to make incredibly educated guesses about the wider population.
Let's ground this in reality with a dummy dataset. Imagine we're looking at a lineup of 15 student suspects. We have different data points for each subject: their age, gender, exam score, and weight. This is our raw evidence. This specific group of 15 individuals is the exact sample we're going to interrogate to see if we can find any hidden patterns.
As we look at those columns of evidence, we need to categorize them. And let's translate some mathematical jargon into plain English here. We have two main types of variables. Discrete variables, think of them as distinct buckets. Things like gender, or whether you got an A, B, or C on a test. You either fall into one bucket or another. On the other hand, continuous variables are measured on a sliding scale. This includes things like a student's precise age down to the day or their exact weight. Knowing whether you have a bucket or a sliding scale completely dictates exactly how you investigate the clue.
Which brings us to Section 2, describing your sample, organizing the evidence. This is our next big step. When we want to summarize discrete categories, like a gender breakdown, we use frequency. That is literally just counting heads. We also use relative frequency, which gives us the percentages. In medical research, this foundational summary of who is actually in your study is typically referred to as Table 1. It's basically the mugshot of your sample, establishing exactly who you're dealing with before the heavy interrogation begins.
But what about our continuous variables like weight and age? Well, we describe those sliding scale clues using two distinct methods. First, measures of location, like the mean, median, and mode, which tell us where the middle of our data lies. And second, measures of dispersion. This includes standard deviation. To strip away the jargon, standard deviation simply represents the spread of our values around the average. And in a medical context, this is absolutely vital. Like an average blood pressure of 120 is great, but if a patient's spread means they're wildly swinging between 80 and 160 all day, yeah, that's a medical mystery we need to solve.
All right, Section 3, the leap of inference, or guessing the truth. This is the climax of the statistical process. To make that leap from our sample to the vast population, we have to start with an assumption. Enter the null hypothesis, usually written as HO.
The null hypothesis is your baseline, honestly, kind of boring assumption that absolutely nothing special is happening. It assumes there's zero difference between your specific sample and the overall population. Essentially, scientists dedicate their entire careers trying to confidently prove that nothing interesting is happening is a complete lie. Finding the evidence to reject this boring default is exactly what we're testing for.
Moving on to Section 4, Testing the Hypothesis. Battling the villains of error. This is where things get tense. Whenever we test our hypotheses, we face the inherent risk of making critical, study-ruining errors. Meet the two villains of our data story. A type 1 error is like pulling a false alarm. Our statistics accidentally tell us we've found a meaningful difference, or maybe a cure, but in reality, it's just a fluke of the data. There's no fire. A type 2 error, on the other hand, is the hidden monster. This is a false negative. This is when there actually is a real difference or disease out there in the population, but our test entirely misses it.
Now, if you've ever read a scientific paper, you have definitely seen this number, 0.05, the famously confusing p-value. But what does it actually mean? It represents the standard 5% risk that researchers are mathematically willing to accept for committing a type 1 error. It's also known as our alpha. We're basically saying, hey, I am willing to accept a 5% chance that my positive finding is actually a false alarm. It's essentially the mathematical margin of error a detective accepts for accidentally arresting the wrong suspect.
Think of testing a hypothesis like throwing darts. The population mean, the ultimate truth out there in the real world, is the red bullseye. The sample mean, our specific data from our suspects, is where our dart actually lands on the board. Power is our ability to consistently hit that bullseye when we're aiming at it correctly. It's the probability of correctly detecting a real difference without making a type 2 error.
So, how do we increase our power and hit the bullseye more often? Well, as our source material states, power is a function of sample size. It's incredibly intuitive. If you throw more darts, meaning if you increase the number of people in your sample, your hits visibly tighten into a cluster. You massively reduce your risk of a type 2 error, and you heavily increase the sheer investigative power of your study. Simply put, bigger samples equal better aim.
Finally, we reach Section 5, Choosing the Right Test. This is our final toolkit. First up is the t-test. You use the t-test when you want to weigh or compare continuous variables between two distinct groups. For example, in a medical setting, you might use a t-test to compare the continuous blood pressure levels of a group taking a new drug versus a group taking a placebo. In our dummy data, running a t-test successfully proved that the continuous variables of heights and weights were significantly different between the men and the women. Next is the chi-square test. You use this to check for associations between your discrete categorical variables, those buckets we talked about. In our student data, you might ask, are men or women more likely to score under 80 on the exam? When you run the chi-square test, it checks the buckets, and it reveals that the p-value is well over 0.05, meaning there is absolutely no mathematically significant association between a student's gender and their ability to pass the exam in our dataset. But what if you have 3, 4, or 5 suspect groups? You can't use a simple t-test for that. Actually, scratch that. That's exactly where ANOVA, analysis of variance, comes in. You use ANOVA to compare means across 3 or more groups. In our data, it initially looked like lighter students might have performed differently on the exam than heavier students. However, by grouping the students into 3 distinct weight categories and running an ANOVA test, the researchers definitively determined that test performance wasn't actually associated with the students' weight categories at all. It was just statistical noise. Finally, we have regression. You can think of regression simply as drawing a line of best fit through your data points. It determines how an outcome changes when independent variables change. In a hospital, a regression line might track how a patient's recovery speed changes as you slowly increase their medication dosage over time. When we plot weight against exam grades for our 15 students and draw that line, the regression shows a very weak, totally insignificant correlation. Again, proving that gaining a kilo of weight doesn't reliably change your exam score. Let's step back and look at the whole picture. We've successfully closed our case. We started with raw, messy clues. We cleaned them, categorized them as discrete or continuous, mapped them out, battled the villains of statistical error, and applied the precise mathematical interrogation techniques. We moved all the way from stating a valid question to confidently interpreting and communicating a reliable conclusion. Biostatistics isn't just some hurdle in a medical journal. It's literally the language of scientific truth. By understanding populations versus samples, the power of a p-value, and the right test for the right clue, you are no longer just a passive reader. You hold the detective's toolkit. So I'll leave you with this.
The next time you see a medical headline claiming a massive breakthrough, are you ready to interrogate the data? Thanks for joining me on this explainer. Keep questioning everything.